Hey y'all, this lesson is on finding confidence intervals for a population mean when the population standard deviation is unknown. So in my previous video, we did known, and in this video, we'll do unknown. So this is a little bit same type of process. It's just that a lot of times the population information is not readily available. So a lot of times we use this method instead. And that's what we're going to learn. This actually has a really kind of fun story behind it. There was a guy named William Gossett, and he developed this distribution for Guinness Brewery. And the brewery didn't want the information published, so he published it under an anonymous name. He called it the student's T distribution. So it's a letter T, lowercase. Pretty fun story. And then I just kind of summarizing some of the things that we've already looked at previously in lessons. We have the standardized version of X. We called that a z-score. We were given a value, the population mean, and the standard deviation. Then we have a standardized version of X for a sample size N when given X bar. That's what we found in the last one. We have the standard deviation of the sample mean instead. And then now we're introducing the studentized version of sample mean, where the population standard deviation is unknown. We use the sample standard deviation instead. So we have a normal distribution is identified by its mean and its standard deviation. A T distribution is identified by its degrees, of freedom. And you may ask, what is degrees of freedom? We abbreviate that DF. DF is found by N minus 1, where N is the sample size. So a degree of freedom is, the simplest way I can put this is the amount of freedom that you have in making assumptions. So for example, if you have 4 quizzes in a class, then, and if you score an 80 on 3 of them, then we could probably go ahead and assume that you're going to make around an 80 on the 4th one. So we would have 3 degrees of freedom, 4 minus 1. And so they use this for the T distribution. It is roughly mound-shaped. It's a little more spread out, but the more degrees of freedom you get, the higher, the tighter the tails go, the narrower it gets, because the degrees of freedom are based on your sample size. And as your sample size gets larger, that's going to tighten up your data so that it looks more normal. So there's a little sketch of it. A couple things that you need to note about a confidence interval when the population standard deviation is unknown. And remember from the last lesson, these are really important, so we don't want to just gloss over these. You cannot do a confidence interval when the population standard deviation is unknown unless the sample is randomly selected. If it does not say that it was randomly selected, then you cannot do it. And then also the sample size must be large, which we know is greater than or equal to 30. If it's not large, the population must be normally distributed. So if the problem or the situation doesn't say anything about it being normally distributed or not, you have to pay attention to the sample size. If the sample size is less than 30 and it says nothing about the distribution, then don't do it. Don't find a confidence interval. If it doesn't say anything about the population distribution and it says there were 1,500 samples, then proceed, go on. And keep in mind that the sample size can be small if the population is, I've already talked about it, normally distributed. So if there are 10 samples, but it's normally distributed, proceed. To calculate the confidence interval, we have to look at a t-table. If you have a textbook, then this will be in your textbook. It is a t-table. And remember that we find alpha by doing 1 minus your confidence level. So we have to know the confidence level. And we also use alpha over 2. Now, I didn't put something in here that I want to point out. What we're finding is, just like with the z-scores, we're finding t sub alpha over 2. And that represents the right tail. So I drew a little picture over here so that you could see what we're doing, just like with the z-scores. This little piece over here is alpha over 2. And what we're looking for from the table is this value. Now remember, it's symmetric to the -1, which this little tail is also alpha over 2. So you can do it 2 different ways. So let's say, I think we have an example here at the bottom. What critical t-value would we use for a 95% confidence level in a sample size of 25? There's a couple things we need to note here. If it's a 95% confidence level, we're doing 1 minus 0.95, which means that the tails, that's alpha, is 0.05. Which indicates that half the tails is 0.025. So this is t sub 0.025. And then the degrees of freedom is n minus 1, which is 24. So these pieces of information are going to help us with our t-table. Have a bit of tea. I shouldn't have done that. Okay. So for our alpha, we're going to go over to 0.025 and go down to 24. We're going to see where those meet. I marked it out right here. 2.064. So that's our critical t-value. And if you are having trouble with the numbers I wrote and how I found that, you can draw your rough sketch. We have 0.95 in the middle, 0.025 here. So that is like that. And that's actually going to help us on the next part. You can use your calculator to find t-values, but when you use your calculator, first of all, you have to use inverse t because we're doing t-values. When you type it in, depending on your calculator, I have an older one, you have to do a little bit of work before you can type it in, unless you want to deal with the negative number, which is fine. So if you had typed in 0.025, then it's going to spit out a negative t-value, and you have to know to change that to a positive t-value because we're looking for the right tail, which is fine. Or you can draw your little picture, and this area to the left is 0.975. So we would go to, I think it is second vars, go down to inverse t. I'm going to type in 0.975 and then the degrees of freedom. Not the degrees of freedom, the sample size, I think. No, wait. Yeah, degrees of freedom. I'm sorry. Whoop. There we go. So I'm going to go down to inverse t, I'm going to type in 0.975, that's my area to the left of my critical value, comma, degrees of freedom. Takes a minute. And if I round it, I get to 0.064. So you can see you can do it either way. But if you use your calculator, if you have an older calculator like I do, you have to know what to type in. And if you type in the wrong piece, like if you had typed in this piece, 0.025, you're going to get negative 2.064, which is fine. You just have to know that we're looking for the positive t value. Okay? Okay. That's why it helps to draw a picture. Art in math. Confidence interval for population mean when standard deviation is unknown is found by this formula, which you might recognize a little bit. We have x bar, which is our sample mean, plus or minus, which gives us our upper and lower bounds, our critical t-value, our sample standard deviation, since we don't know the population standard deviation, and sample size. So this is all based on a large sample or a normally distributed population. So a few reminders here. X bar is the sample mean. S is the sample standard deviation. N is the number of samples. Not too bad. Use a t-table or your calculator to find the critical t-value for 95% confidence level. We actually did that on this page, so you can use that instead. 2.064. You would do inverse t of 0.975. Uh-oh. We can't if we don't know the sample size. So, I'm sorry. I was assuming it was the previous problem, but it's not. We're using this problem here, and the sample size is 36. So that's my bad. N equals 36. So degrees of freedom is 35. And now use your t-table or your calculator to find the t value. You try. I got about 2.03. That is based on a left area of 0.975. If you're doing a calculator, if you're doing the table, you're doing 0.025 with 35, as your degrees of freedom. Make sure I did that right. Yeah. The table I included here didn't go down to 35, so you'd have to use your table from your book, or you can Google a t-table and that'll come up. So if you're using your calculator, you would type in inverse t, area to the left, degrees of freedom, and that'll give you the 2.03. 2.030. So now we can use our formula with the given information to help us find the confidence interval. So you go ahead and try it, interpret it, and come back. Press pause, try it, come back. So you should have gotten 20 plus or minus our critical t-value times standard deviation over square root n. And then when you figure that up, you get 2.03 times 0.5, which is 1.015. And then you do 20 minus that for your lower bound and 20 plus that for your upper bound. So your interval goes from about 18.99 to 21.015. So what does that mean? We are 95% confident that the population mean is between those two values. And then what was the margin of error for this confidence interval? if you'll remember, the margin of error is the plus or minus at the end. And that's kind of our wiggle room with our confidence interval, confidence level of 95%. So we're saying it's give or take 1.015. We know that the population mean is somewhere in here. So we have the sample mean plus or minus the margin of error. Okay, next page. You can do this in your calculator. Obviously, there's the steps. In the last lesson, we used a Z interval. And since this is a T distribution, we're going to use a T interval. And then you'll input all your information. And then I want you to try these. You can do them by hand or with a calculator. And then we're going to make some observations at the bottom when we're done. So go ahead and try it, and then come back and check your work. So after doing your intervals, you should be getting these values. So go ahead and check them. Make sure you're getting the same thing. And then the interpretation is a lot of repeating. So we are 95% confident that the population mean is between these two values. We are 95% confident that the population mean is between, and so on for all of them. And then for the two values, you just put your lower and upper bounds. So that's it. But we do want to make some observations down at the bottom. So based on your table, based on your results, why don't you try to note some of the differences and how it changed when certain elements changed. Go ahead and fill out these questions and then come back. Your wording might be a little bit different than mine depending on what you saw, but basically this is the gist of what's happening here. When the mean changed, it basically just shifted over our confidence interval. So it shifted the center. And the example that shows that is the first two boxes, everything is the same except for the mean. And so if you'll notice, the mean increases by 5. And if you look at the confidence intervals, they also increase by exactly 5. So it was literally just shifted over 5 on a number line. And then how did changing the standard deviation affect the interval? I actually went in, I didn't have one where everything was exactly the same except for the standard deviation. So I just made one. I used the first box and changed the standard deviations to something larger. When I had a larger standard deviation, it made my confidence interval also larger. It spread it out. How did changing the sample size affect the interval? When you have a smaller sample size, it actually spreads out your interval. Because remember, with a larger sample, we know more about the population. And so we're going to shrink in that interval because we're going to be more confident about what the mean is. So when we have a smaller sample, it's like, we don't know as much about the population means. We're going to spread out this interval and have a bigger range. And then lastly, how to change in the confidence level change the interval. The smaller the level, so like 90%, the smaller the interval. So remember in the previous video, we had a confidence level of 99%. It made that interval wider because we're saying we are almost 100% confident. So we're going to make our range a little bit bigger so we're more positive that it's in there. If I say I'm 90% sure, then we can have a smaller interval because we're less sure. So that is all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know and I would be happy to help. Bye, y'all.